Okay, so welcome back to CET236 Summer 2021 edition. I was out of my usual office last week, as you probably could tell from the video, but I hope we managed to get through enough with that. As of last week, apart from maybe transients, which I'm going to talk about next week, as of last week, we've talked about everything we need to talk about. There's two minor changes that I need to go through, one tonight, one next week. But all of the algorithms, all of the ideas, we've covered everything. So the wrinkle I'm going to throw at you tonight is that everything we've done so far with resistors can also work with other passive devices. You remember we talk about the passive sign convention? Well, there are two other passive devices that we can use in circuits. One of them is an inductor, which is effectively just a coil of wire. And one of them is a capacitor, which is like two flat plates separated by some medium, some electrolyte. And the only difference between resistor-only circuits and circuits with resistors, inductors, and capacitors in them is that now it's possible for the resistance, and that's why this is called impedance, because it's a bit different. It's possible for the resistance to be complex, right? So that's why I talked a little bit about complex numbers earlier in the semester. So that's where we are. I decided after the fact that anything that was due last week is also not really due until 26th, just like everything else. And I've got a slight modulo on that as well for the transient homework and lab. That can be due a little later as well. Course evaluations. Every time you log into Blackboard, you will probably be bugged by the fact that there is a course evaluation available for this course. Please give me your feedback, even if it's negative. If it is negative, try and give me some way to improve, right? And so that's why I request constructive feedback. As students, you see more professors teach than I do. So if there's something that somebody else has done that you think could be done, I could use in this course or any other course I teach, but this course in particular, please let me know. I'd love to hear about it. I've taken a few pieces of feedback over the last few semesters, particularly since COVID hit and we've been doing things remotely. But let me know. And for those two who have already submitted without me asking, thank you very much. I appreciate any and all feedback. So really, apart from maybe transients, which I'll talk about next week, we've done everything. Everything that you really need to know about for this course is in the topic list on the left-hand side of this slide. That's what this course is about. The highlighted yellow stuff on the right-hand side is basically exactly the same as the left-hand side, except now all of those resistors can be complex and they're no longer resistances, I'm going to call them impedances. And the stuff that was scheduled to be due tonight is homework 5, homework 6 and lab 7. As I've said last week, if you submit them by that deadline, you can get a 5% bonus, but I'm not going to stop submissions until 11:59 p.m. next week. So please get them done one way or the other. I'm going to work through these, particularly lab 7, because it's there's some bits to it that make life a little hairy to do the lab. But it's not that bad. It's just how to set up LT Spice to be able to do the maximum power stuff. And then next week there is the Phasors homework and Phasors lab due, and the modulo that I mentioned earlier for the transients homework and the transients lab. The latest I can really make those two submittable is Sunday, August 1st. That spreads the load out a little bit compared with maybe doing it by the original schedule, right? So they're down here. But there's still a reasonable amount of work to get done. So hopefully that spreads it out enough. I have to get final grades in by August 2nd at 11:59 p.m. So there's not much wiggle room. Let's just grab that let's grab so there's that, and I'll kill it, and then I'll just post that into there we go. Okay, so because of various timing issues, I still only have about half the students have taken the midterm, so it's a little late, but anyway, it is what it is. Everybody's booked. I'm going to finish those off this week. I won't release your grades for the midterm until after everybody's taken the midterm, so I'm going to turn off visibility on that column tomorrow morning once I start grading. Yeah, there's that. I have released the final, so you should be able to see exactly what you're in for with the final. And as I said, you must take it during next week. And in any event on or before August 1st. Let me just have a quick look at what's in the final paper. I may change it a little bit just in terms of the formatting, but the questions will be pretty much the same. The main thing I'm going to change is this front page to make sure I get everything correct there. But the topics are phasors, which is basically dealing with complex voltages and currents and impedances. All right, there's 4 different options of the questions. I will ask you one of these options. I'll ask you one option from each topic area, just like I did with the midterm. First one is phasors. The next topic is superposition, but it's not just superposition with resistors, it's superposition with the added complexity of the things we're talking about tonight. Inductors, which look like this little coil thing here, and capacitors, which look like these 2 plates. There's also a question about transients, which we're talking about next week. We've talked about, for most of this course, we've talked about circuits with constant voltages and currents. The things we're talking about tonight are voltages and currents that are sinusoidal or cosinusoidal in shape. Transients span between those 2 extremes. Right? Effectively, they give you a way to how a circuit with resistors, inductors and capacitors in them change with time if the circuit changes. Another topic is Thevenin equivalent circuits. And another topic is Norton equivalents using source conversions. And all source conversion means is you can replace a Norton equivalent circuit with a Thevenin equivalent circuit and vice versa. So you can manipulate each of these. For example, here in option 2 we've got a 20 ohm resistor and a 40 volt supply in series. We can replace both of those with a Norton equivalent, which will be a parallel current source with a resistor in parallel, the same 20 ohm resistor in parallel with it. And then you can change the shape of the circuit by swapping between Norton and Thevenin equivalent circuits in order to simplify the circuit. But the aim is to eventually get, for question 5, to a Norton equivalent where you've got a current source and a parallel resistor. Okay, any comments, questions about any of the stuff that I've just gone through, the due dates, the midterm, the final? No? Okay, if everything's good there, then let me go back to the notes from tonight. And let's talk about, first of all, let's talk about homework 5. So let's go to web work and have a look at that one. So what was homework 5? Superposition, I think. Yes, superposition. Okay, so remember what superposition is about. Superposition says that the effect on a circuit of any independent source happens regardless of whether any other independent sources are in the circuit or not. So what we can do is we can work our way through the circuit with lots of independent sources and keep just one of them and replace all the others with their ideal sources, which sets whatever parameter it is, voltage or current, to 0. So the ideal source for a voltage source sets the voltage across the source to 0, so it replaces the source with a wire. And for a current source, if we turn the current down to 0, that replaces the current source with an open circuit. Okay, so for this one, the first part is how many subproblems. Well, that just means how many independent sources are there. Well, there are 2. Okay, so I got that one right. And then the question gets a bit more complicated. And we've got to analyze the effect of Vs to find I out 1. Right, so for I out 1, so what we're going to do is we're going to replace IS with its ideal, which is an open circuit, and just look at the effect of Vs. So that makes this circuit turn into something like that, where that's R1, R2, R3 and R4, and this is Vs, and we want to know what I out 1 is. Okay, so let me just move that over here, do that, bring that up, does that work? So, Bob, how would you go about figuring out what I out 1 is?
I would use mesh analysis, and you have 2 meshes. Find the second current mesh, and that would be I out.
Okay, that's a pretty good approach. right? And we can do that. So that could be I1, and that would be I2, or we could just call it I out because it is I out, right? Because there's only one mesh going through where I out 1. Let's call it I out 1 just to make sure we know it's not the real answer, right? And yeah, that would allow us to get a solution. Excuse me. So let's write that out. So we get, for the I1 loop, we get minus Vs plus I1 R1 plus I1 minus I out 1 R2 equals 0. And then the other one, I get I out 1 minus I1 times R2 plus, and I'm just going to combine R3 plus R4 to I out 1, and that equals 0. There's no voltage sources there. Okay, and we can grab the numbers. What's Vs? Vs is 24 volts. So let me just write these down. That's 24 volts. And then I've forgotten what all the others are. R1, so 8 to 2, 14. One thing to notice is I know some people have been missing out the fact that there's a K there, right? So some of the numbers that they've been getting are out by a factor of 1,000, one way or the other. So make sure you note whether there's a kilo in front of the capital Omega, and that one's 3 milliamps. Okay, so then we can redo the blue one and we get minus 24, excuse me, and then plus R1 is 8 and R2 is 2, so that's plus 10,000 I1, and then minus R2, which is 2,000 I out 1. Equals 0. And here we've got R2 plus R3 plus R4, so R2 plus R3 plus R4, so that's 18,000 I out 1, and minus I1 times R2, so that's minus 2,000 I1, and that equals 0. So then we can just cobble that all together and get 10,000 minus 2,024, because I take that onto the other side, and then minus 2,000, 18,000, 0. So then I'm just going to type that into Matlab. I'll show you the, move Matlab over to the screen you can see shortly. Right, so that's what I need to do there. And I might need to save that. Actually, let's just change that to format long. And then we get that I out 1 is 272.7 microamps. Or let's go with just the number in amps, and let's see if that gets and remember to use the units. Okay, so we got that one right. So that's the first one. And let's have a look at the second one. Right, so I'm sorry, I even talked to you this afternoon. I've forgotten. Aaron, sorry, Aaron. What do you think we do to do the next part of this question?
So we found our solution for our current, so then we would suppress our voltage.
Mm-hmm.
And then I think we use nodal analysis because we're going to end up with a circuit that has basically one node. So I think it'll be easier to do than mesh analysis once it's all said and done.
Okay, so let's see if we can draw out the let's see if I can draw out. So we're replacing VS with just its ideal, which is just a wire. And then we get those. We get that. And then we get R2 is there. And we get our current source like that. So that's again R1, R2, R3, and R4. And you're suggesting that we just do nodal analysis, right? And that way we can
It just seemed that, like, because you have three, if you do that with mesh, you'd end up with three meshes. If you did it with nodes, you'd end up with two.
yeah, I agree. And the mesh is going to be a super mesh because of the two of the meshes are going to go through the current source. So that makes sense. So let's have a look at what happens. Well, what I like to do with these is to make sure we figure out what direction everything's going in. And let's do it that way. And then at node A, and it's the KCL, remember, if we're doing nodal analysis. So that's going to be IR1 plus IR2 plus IR3 equals 0. and it's going to be, because of the directions, it's going to be 0 minus VA on R1 plus 0 minus VA on R2 plus VB minus VA on R3 equals 0. I think that's right there. And what was it? 8, 2, 2 and 14. And then let's just rearrange that so we get minus 1 on R1 plus 1 on R2 plus 1 on R3 times VA plus 1 on R3 times VB equals 0. And then the KCL at B, we get minus IR3 minus IS plus IR4 equals 0, because IR3 is going out, IS is going out, IR4 is going into B. And IR3 is exactly what we had before, so it's minus VB minus VA on R3 minus whatever it was, our 3 milliamps, and then plus 0 minus VB, which is 0 on R4 equals 0, and then we can rearrange that a little bit to get what's that, 1 on R3 times VA and minus 1 on R3 plus 1 on R4 times VB. I think that's right. And then I can take the 3 milliamps over the other side, so it becomes positive. So then what have I got? I've got what is it? 822 and 14. So minus 1 on 8,000 plus 1 on 2,000 plus 1 on 2,000 times VA, and then R3 was also 1 on 2,000 and a 0, and then a 1 on 2,000, and then a minus 1 on 2,000 plus 1 on 14,000. And then the, oops, I probably made that too far over, so that's 0.03. And then I can type that into Matlab. So let's just type it in directly as I've done it there. So minus 1 on 8,000 plus 8,000, not 800, plus 1 on 2,000 plus 1 on 2,000, 1 on 2,000, 0, 1 on 2,000 minus 1 on 2,000 plus 1 on 14,000, 0.003 for 3 milliamps. So that's the way I wrote it out in Matlab. I think that's correct. And that seems quite large. Oh, they're voltages, that's all right. So they're voltages. But the thing I want is I actually want, now this is something a little tricky, right? The thing I actually want is the current going in this direction. So in this case, I out 2 is just going to be VB on R4, which is minus 8.5909 on 14,000. Let's see what that is. Don't know, what did I do? It's not letting me type in anything. There we go. For some reason it is now. So it's that on 14,000, which is point minus, right? So let's just pull out the numbers that we need, right? So that's that one. And we want I out 1 is equal to R1, and it's going to be 2, 3. And I out 2 is going to be R2, 2, 3. That's the voltage, but we want to divide it by R4, which is 14,000. Okay, so let's get the 200.27 22. Did I write it down what I got before? I don't think I wrote it down. Okay, and then the didn't write it down? No, let's write it down. So the first one that we got was I out 1 equals 0.2 7 2 7. It's going to be milliamps. And now the one we've got now is I out 2, which is minus 0.6136 milliamps. So let's see if that comes through. 6136. Okay, so that looks like it's good. And then I know the answer. Let's try starting from scratch. And we're back at Bob. Bob, how do we get the part 3 answer?
You would add those two together.
Yep, exactly. So let's not try and do it in my head. Let's grab Matlab again. And
how do you display more precision in Matlab?
I used, on the command line here, I used the command format long.
Thank you.
Okay. Yeah, it doesn't necessarily do a good job. Okay, so it's minus 3.049 by 10 to the minus 4.
So I think 90% of the problem I was having with that I talked to you about was it not displaying far enough.
Right, and I mean, with a lot of these, you really do need 4 significant figures worth of accuracy, particularly in the intermediate results, in order to get any level of accuracy in the final result. So yeah, that can be a problem. So let's just go with those. And I've got to figure out now, so it's going to be 1, 2, 3, 4. Is that right? Yeah, we're all good. Okay, so we, in order to get the final result, we just have to add those two up. Now, you could solve this particular circuit directly using mesh analysis or nodal analysis or whatever, but the aim is to understand superposition, right? So you could have solved this question as a check using one of the other techniques. Was there a question there?
Professor, I see that you've already done problem 3 in this homework set. Was that in a previous video that you had put out?
I am not sure. I'm
currently stuck on that problem and can't figure out where to go. If you're able to kind of walk through this one again,
sure.
I would appreciate it.
Sure. I was going to do them all. So let me do problem 3 now, just so it's there. So how many sub-problems? Just like the other one, we've got to figure out how many independent sources. This one we've got 3 sources, but only 2 of them are independent. I2 is that diamond-shaped thing, so it's a dependent source, right? So the sub-problems are to analyze the effect of Vs and analyze the effect of I1. So let's see if we can do that one. Okay, so the first one, analyze the effect of Vs. So we're going to replace I1 with its ideal, which is an open circuit. So we just get a circuit that looks like this. Now we have to keep I2 every time, right? Because it's a dependent source. And we're removing I1, so that's all that we have. So that's R1, R2, VS, and I2. Okay. Can you mute, please? Okay. Feel free to unmute if you've got a question, but if you don't have a question. Okay, so now what do we got to do? We've got to find V out 1. Okay, so I'm tempted to take the previous approach, right? Because we've got to and use nodal analysis for this one, right? Because at A we've got VA equals minus VS, right? There's a plus sign there, so we're going down to get VA, so that's a freebie. And then at B we have all of those currents that I've just defined going through, I2 plus IR1 plus IR2 equals 0. And that's going to be I2. In fact, let's just go back and look at what I2 is. I2 is 3.4 IX. Okay, so let me just and IX, in fact, I've made my definition of IR1 go the wrong way, right? So IX is equal to minus IR1, the way I've defined it up here. So what we can what that means is our I2 is minus 3.4 IR1. Okay, so then we get that that's minus 2.4 IR1 plus IR2 equals 0. And then we can just look at what IR1 is. It's VA minus VB on R1. And IR2 is 0 minus VB on R2 because of the direction I've defined the current to flow. And then I've forgotten what my R1 and R2 are, so let's go back to, so 4 and 20K. So then what do we get? We get 1 on 4000 VA. Actually, minus 2.4 on 4000 VA plus 2.4 on 4000 minus 1 on 20,000 VB equals 0. And then I've forgotten what VS is. Let's go back to see what VS is. VS is 24 volts. So that means that this is minus 2.4 on 4000 times minus 24 and then I can maybe rearrange it and say that VB equals minus 2.4 times 24 divided by 4000 divided by 2.4 on 4000 minus 1 on 20,000. Let's see what Matlab gives me for that.
If you're moving the voltage, the AVA over, wouldn't it be positive on top there? Or am I missing a step?
Well, it's
Oh, you have negative times.
negative times negative on this side.
Drop my negative.
Right, and then when I bring it over the other side, it's going to be negative again. Okay. Okay. So let's just save that into a new file. And what do I want to do? I'm going to say that VB equals, and I'm just going to write it out exactly like I've got it there, minus 2.4 times 24 divided by 4000 divided by, open parentheses, 2.4 on 4000 minus 1 on 20,000. And that gets me minus 26.181, but 4 significant figures is probably enough volts. Let's just check that that tallies. Yep, there we go. That's the answer I got last time. Okay, so let's I know how to do it. So Aaron, how do we do the second one, the effective I1? No response?
Try to go. So we just did. Yeah, we ignored the current source. So this time we would ignore the voltage source, the VS.
Right. So what does that look like?
So that would put 0 voltage at that left branch we simplify it to just be let's see how this could look. Can we simplify it so that it would just look like a rectangle, and then the current on top with that current and resistor through the center?
Pretty much, yeah, I think that's right. So let's just draw the outside first, and then we've got that like that, and then we've got to have our current source down here. Okay. So I would be tempted to just do nodal analysis again, right? Because really there's only two nodes, A and B. And the thing we want is VB. So that's 4k ohms, that's 20k ohms, and I've forgotten what the current source was. Current source is 14 milliamps. Okay, so let's choose a different direction. Because that current source is going out, let's choose all of the others for going out as well. We can't choose that one. So now we've got, we don't get a freebie this time, right? We've got a IR1 flowing into node A, and then I2 flowing out of node A. And just like before, well now because I've chosen this going in the same direction as IX, I2 is just 3.4 IR1, so it's IR1 minus 3.4 IR1 equals 0. Which is kind of interesting. So I think that means IR1 is 0. So then we can do the currents at node B, the KCL at B, right, and they're all flowing out except for I2. So we get minus IR1 plus I2 minus 14 milliamps minus IR2 equals 0. It should be IR1. So that's minus IR1 plus 3.4 IR1 minus 14 milliamps minus IR2 equals 0. So what's that? That's 2.4 times IR1. IR1 is VB minus VA on 4000. And then it's minus IR2. IR2 is VB on 20,000. And that equals 14 milliamps. Now really, because we already know this, we know that this is 0. Or VA equals VB, I think is what that's saying. So then we just get VB equals minus 20,000 times 14 by 10 to the minus 3. Now that seems wrong. Anyway, let's see how far we can take it and figure out what our problem is. Yeah, that's going to be wrong. So I've done something wrong. What have I done wrong? You know what I've done wrong? There's still current flowing up through here, right? So that's what I've done wrong. Okay, it's about time I took a break. Obviously I missed that. Let's take a 10-minute break, and when we come back I'll fix the issue that I just caused by not taking into account that that extra current in the KCL for node A. Before I do that, any questions so far? Okay, let's take that 10-minute break. I'll put a 10-minute timer up. And I'll be back shortly.
Professor?
Okay, so let's review what I was doing before, and what I'm going to do is I'm going to see if I can grab that and start again. That way I get to keep my mistake so we can compare it later on. Right, so there we go. Let's just back up a little bit and look at where node A is. Just go with an orange, right? Even though, and I've told you this before, right, that right, a node is an area of constant voltage.
Professor, you're still muted.
I'm
if you're
still
trying to
muted.
speak.
Okay. Okay, so I've just taken the picture. I'm going to leave my mistake up there, but I thought it might be good. In fact, let me put my mini-me back on. Here we go. It might be good to have a look at why I made the mistake. Right, so the mistake I made was looking at the currents flowing into node A. And remember, a node is an area of constant voltage. Even though I draw them usually as a dot. Ooh, what's happening there? Right, even though I usually draw them as a dot, really, node A is all the way around here. Right? So I have to take into account all the other places that I get currents. And then similarly, node B is all of that stuff. So let's try that again. Okay, so node A, we have, not A, node A, we have minus I2, right? Because it's coming out of the node, it's going that way. We have plus IR1, because it's going that way. We have plus 14 milliamps. And we have plus IR2. And then we have to go back to say that I2 equals 3.4 IX, which in this case is 3.4 times IR1. Right, so that means we get a minus 2.4 IR1 plus IR2 equals minus 14 milliamps. And then IR1 is just VB minus VA on 4K. And then IR2 is VB on 20K. Okay, that looks a little better now. I think I did node B correctly before. Let's just compare it, right? Except, well, I got the first couple of lines right. Once I started relating it back to my node A result, it's wrong. So let's look at node B. Right, so node B has minus IR1 minus 14 milliamps minus IR2 plus I2 equals 0. And again, I2 is 3.4 IR1, so that's going to be 2.4 IR1 minus IR2 equals 14 milliamps. I have a horrible feeling we might have a problem.
Why do you think that?
So, in order to solve for two unknowns, you need two independent equations. And I think what I'm about to see is the equation I get for node B is the negative of the equation for node A. So they're not independent of each other. So I'm starting to think I made yet another mistake, and that other mistake is that really there's only one node in this question, because node A is the reference node, so we know the voltage is 0 already. But let me just do the last little bit, but I'm pretty sure that's what's going to happen. Right, so this is going to be 2.4 times VB minus VA on 4000, and then minus IR2, which is just VB on 20,000, equals 14 milliamps. And it looks to me that this and this are just negatives of each other. So they're not independent. So basically there's an infinite number of solutions to that. So what we've got to do is try again. And this time I'm going to have a reference node.
There was a reason I didn't like this problem.
Well, now you know. Okay. So now that's
Professor, couldn't you just use your equation you had before and just set voltage A to 0 and you'll solve for voltage B?
yeah, that'll work. That'll work. What I was wanting to show is just maybe redrawing the circuit so that it's a bit more obvious, right? So what we could do is, but I'll take that approach. I think that's probably simpler. But let's just have a look. If we redraw it so that we get basically node B at the top and the reference node down here, then what we should end up with is something looking like this. Right, there's that. And then there's R1. This is I2. There's I1. And then there's that's R2. Okay, and then I should just be able to write down the equation for it, which is going to be I2, and let's just make that come down, make that one come down. So minus IR1 minus I1 minus IR2 equals 0. Yeah. I know. Let's come back. Wow, that's different. So what was I2? I2 is 3.4 IR1, so that's going to be 2.4 IR1 minus 14 milliamps, and then minus VB, well, let's just keep it with IR2. So IR1 is then so it's 2.4 VB on 4000 minus VB on 20,000 equals 14 milliamps. So that's going to be 2.4 on 4000 minus 1 on 2000 times VB equals 14 milliamps. And if we go back got a sign wrong for some reason. Not my best evening. It's VB. It should be 20,000. Well, that one I didn't. Yeah, I shouldn't be doing those anyway, I think. Yeah, so if we look at that one, right, if we set VA to 0, we basically get the same equation. This equation is the same as this equation. No, it's gone. Okay, so then my VB is just equal to 14 milliamps divided by 2.4 on 4,000 minus 1 on 2,000, 20,000. And let's have a look at what that does. Where did Matlab go? There it is. So in this case, VB equals 14 milliamps divided by 2.4 on 4,000 minus 1 on 20,000. Okay, so I'm just going to run that one. So it's 25.45, and I think that was what I was getting. Yeah, so 25.45. I apologise for such a long-winded way of getting there. That was on me.
It just makes us feel better that it was hard.
Yeah. So hopefully that gets that one. Let's just have a quick peek at. Well, and then the obvious thing at the end is, again, you just add those two answers for each independent source in order to get the answer for the complete circuit, right? And I think you can see that this one's slightly bigger in magnitude than this one, so it's going to be a little bit negative, so minus 0.73 volts. And let's have a look at inactivity. So superposition, again, how many? 2, right? There's only 2 sources and both of them are independent. So let's check that. And then let's go back to our bingo. So Chris, what do we do? How do we deal with analysing the effect of VS? Let me just pick that image.
Mesh analysis.
Okay, let's oops. Just try that again. So we want to do mesh analysis. Well, so let's start. So what are we doing? We're looking at the effect of VS. So what does the circuit look like if we're just looking at the effect of VS?
It would just be 2 loops with R1, R2, and then one with R2, R3, R4.
Okay, so right, so let's have a look. We'll get R2, R1 rather, R3, R4. That's R1, that's R3, that's R4. And then here we've got R2 and VS. And the output we're looking for is I out. Okay, so yeah, let's see about mesh analysis. So Chris, can you talk me through how you would define the meshes for this circuit?
I would the the mesh you're in right now be going clockwise.
Mm-hmm. Okay, that's one.
Then counterclockwise in R2.
So why counterclockwise?
Just because then it's going into the negative on the VS and out the positive.
So you can do that, right? That's perfectly okay. And let's do that. So let's make it go counterclockwise. The only thing I would say is that means that I out is minus I2. Just make right. Just make sure you're aware of that. So we'll get the answer for I2, but then we'll have to negate it for getting the I out 1. In fact, that should be I out 1, right? Because we're doing superposition. Okay, so that's all right. So then the I1 mesh just gives us I1 R1 plus I1 plus I2 R2 minus VS equals 0. And I've forgotten what all the numbers are, so let's go back and have a look at the numbers. 220, 260, ooh, they're all over the place. 220, 24 volts and 100 milliamps. So let's just, so that's 100 milliamps. That's 24 volts. And it's 220, 260, 360. $220, 260. What did I say? 360? And then the last one is 240. Okay, so then we can write that down. So that's R1 is 220 and R2 is 260, so that's 480 I1, right? And then plus 260 I2, and that equals 24 volts. And the I2 mesh has got R3 plus R4 times I2 plus I1 plus I2 R2, and again we've got minus VS equals 0. So it's R2, R3 and R4. So 260, that's 560, 620. Don't know what happened there. 620 and 240, that's 860 I2. And then I1 we've just got R2, so it's 260. So that should tell us, this is question 2. Let's just grab another one there. So that's A equals 480, 260, 24, and 260, 860, and 24. Hope somebody's checking my arithmetic. Okay, so that means my I2 is that number. But that means my I out is the negative of that number. So let's just check the negative of that number. Oops, I forgot units. There we go. Okay, so that was that one. And where are we? There we go. So now we've got to deal with looking at IS. So let me play bingo again. Pick on somebody else. Jesse, how do we deal with finding IS? What's the circuit look like for that?
Move the voltage source in the center branch there with R2.
Mm-hmm.
Just be 3 mesh squares, I guess.
Okay, so we've got keep our current source.
Is it? Is the voltage one being removed called the short circuit, or is it the current source being removed called the short circuit?
So the voltage source means that the voltage drop across the source, when its ideal is it's replaced with its ideal, the voltage drop across it is set to 0, right? So that means we've got effectively a short. Okay. Whereas the current source, when you set the current to 0 for its ideal, that's an open circuit.
Okay, thank you.
No worries. Okay, so that's R1, R2, R3 and R4. And we want to again find I out 2. So how would you go about solving this?
Well, this one, I don't think that you'd want to do it as a mesh, right?
Mm-hmm. Yeah, I think that's a bit complicated. I
That would
think
be the nodal.
even that's a bit complicated.
Yeah. Well, then I do not know.
Okay, no other guesses? Okay, so what the way I
You just simplify it into a smaller circuit.
right, so what I'd do is I'd use the current divider approach, right? And I'd replace R1 and R2 with R1 in parallel with R2. And then I'd replace R3 and R4 with the equivalent of R3 and R4 in series, because they are in series. And then
See, I was like this based on our conversation from the other day, and it was not. Well, maybe I wasn't doing something right, but I had parallel in the center R1 and R2, and then series for R3 and R4. But of course, I thought that we had to do this as either mesh or nodal after doing the other 3 examples.
yeah, no, I think I don't think the question asks for a specific way to solve it, right? It's just asking you to solve it, so whichever way works. And you could use mesh analysis, you could use nodal. I just tend to prefer trying the simplest way, and I think so this is because we've got a current source here. I think the simplest, even if it's a voltage source, I think the simplest is just to use a current divider. So in this case, I out 2 is going to be R1 in parallel with R2 divided by R1 in parallel with R2 plus R3 plus R4 times IS, which I think was 100 milliamps, wasn't it? Yeah. So let's see what that ends up being. So that's 220 in parallel with 260 on 220 in parallel with 260, 360 and 240. And let's see what Matlab tells me that is. And this is I out 2. And I'm just going to use a an intermediate variable for R2, 1 in parallel with R2, so that's 1 on 220 plus 1 on 260. So that's going to be REQ on REQ plus 360 plus 240 times 100 milliamps is just 0.1 amps. Sorry, I lost Matlab. Where's Matlab gone? There's Matlab. Right, so that's R1 in parallel with R2, and there's my current divider, because the current divider says that you look at the resistance in the other branch for the numerator, and then the sum of the resistances in both branches for the denominator, and multiply that by the input current. So that's 0.0165 or 16.57 milliamps. Let's see what yeah, it likes that. And then the I out is just the sum, again, the sum of the two numbers. And it should be that and that, just to get it into 4 significant figures, and in current it should be the amps. Okay, so that took a little longer than I expected.
Show your one note one more time.
Sorry?
Could you just show the one note one more time?
Sure, OneNote? Yeah.
Okay, thank you.
No worries. Yeah, so that should get me then, well, that does get me the answer that WebWorks looking for. Okay, let's go back to my week 6 notes. So that took a lot longer than I expected, but we have gone through that. Let's have a, I don't know whether I'll be able to get through all of the rest of it. I do want to spend a tiny bit of time on, well, the new stuff and the lab. Let's just have a quick breeze through the Thevenin and Norton questions, if that works. Right, so here the resistor that is the load is R3, and the aim is to find the Thevenin and the Thevenin equivalent voltage and the Thevenin equivalent resistance for this circuit. The first step in any of these is to remove the load resistor, so remove R3. That's why there's no value given for R3. And then you've got to think about how to find the Thevenin resistance. Remember, there are 3 possible ways. There's the equivalent resistance technique, which says to just, it has a caveat in that you have to have only independent sources. And that's the case in this one. There's the open circuit voltage, closed short circuit current approach, and that one you have to have at least one independent source. And then there's the apply a voltage technique, and all 3 of those sometimes require application of nodal analysis or mesh analysis in order to find the answer. So with this one, I would recommend that the easiest way to do it is, at least to find the Thevenin resistance, is to just use the equivalent resistance technique, because you can replace Vs with its ideal, which is a short. So you've got on the left hand side, after removal of R3, you'll have R2 in parallel with R1, and on the right hand side you will have removed IS, because its equivalent, its ideal, is an open circuit, so you just have R4 on the right hand side. So then the total equivalent resistance for the circuit, looking from where R3 is, remember we've removed it, will be R1 in parallel with R2 plus R4. Okay, and then the other piece is to find the Thevenin voltage. What we just did is found the Thevenin resistance, and the Thevenin voltage, usually you've got to find the open circuit voltage. And again, once we've removed R3 on the left hand side, keeping Vs this time, we just have a voltage divider. So the voltage on the left hand side is just R2 divided by R1 plus R2 times Vs. And then on the right hand side, we just have IS pumping through R4. So that's going to be at a voltage of about 24 volts by the looks of things, R4 being 4 ohms and IS being 6 amps. And then the difference will be between where the minus sign on R3 is and where the plus sign on R3 is, will be the answer. Okay, this one's a tiny bit trickier because it's got a dependent source, so we can't use the equivalent resistance technique. We can, however, use the open circuit voltage short circuit current technique. We have to do the open circuit voltage piece anyway, so that's okay. And it's just a matter of what is V2 dependent on. V2 is dependent on Vx. Okay, so the idea there would be to remove RL and then look at the voltage. Right, you've got a voltage divider between R1 and R2, and V2 is just given by the voltage across R1. So that should be relatively straightforward to find VTH. And then the next piece would be to put a short where RL is, so find the short circuit current. And then the Thevenin resistance is just the Thevenin voltage divided by that short circuit current. Okay, this one has no independent sources, so we can't use either the equivalent resistance technique or the open circuit voltage short circuit current technique, so we have to apply a voltage at nodes A and B in order to analyze this one. And I suspect the analysis will need to be done using mesh analysis would be the easiest, I think. So you go ahead.
I'm actually having a hard time with this one.
Okay, well,
I ended up with my Thevenin voltage being 0, ended up being the correct answer, but I'm just not getting the right resistance. I've added them in series, parallel, tried to put it in 0, putting them one at a time. Like I'm at a loss.
okay, so let me see if I can run through this one. I'll run through this one and then we'll have a bit of a break again. Okay? Okay, so like I said, for this one we've got to use the apply a voltage technique because neither of the other two technique to find RTH. So we'll call this V new, and we have to find I new. And I'm just going to set arbitrarily V new to be 100 volts. Doesn't matter what it is, you get to choose. So let's go with 100. And then I'm going to say I'm going to do this with mesh analysis. Not quite sure why, but let's do that way. Let's do I2 that way. And let's make I new go that way. So this is just I new. Okay, let's go back and get all the numbers. So IS is 24IX. VS is 450IX. and then R1 and R2, oops, it's a cat. R1 and R2 are 414. Okay, so one thing we can say is that Ix is equal to I1 minus I2, right? Because I2 is going that way against Ix, I1 is going in the same direction as Ix. So then let's do the I2 loop, or mesh. And we just get that I1 is in fact equal to 24Ix, which is equal to 24 times I1 minus I2. So we can rearrange that and say that that's 23 I1 minus 24 I2 equals 0. Then let's do the I2 mesh. So that's going to be I2 minus I1 times R1, which is 400, minus 450 Ix plus, now I2 and I nu are going in the same direction, so it's I2 plus I nu times 14 equals 0. So let's see if we can pull that out. So it's minus 400 minus 850 I1, and that's 400 I2, 850 I2, 864 I2. And then just plus 14 I nu. Again equals 0. Oops.
The middle part there, you have minus 450. Are you calling that voltage? Where?
Yes, so it's this term here is minus Vs, right? And Vs is 450 Ix. So minus 450 Ix is minus 450 I1 minus I2. I probably skipped a few terms there, right? This one, this term here is minus Vs. And I think Vs was 450 Ix. Okay. And then the last piece is I nu, and that just says the I nu mesh and that one just says that, what have we got? We've got I2 plus I new times 14 minus 100 equals 0. So 14 I2 plus 14 I new equals 100. So then I should be able to redraw that as, well, let's just do the whole matrix. So 23 minus 24, 0, 0, minus 850, 864, 14, and 0 again, and then 0, 14, 14, 100. So this is the Thevenin. It's Q3, I think. So this time my A matrix is 23 minus 24, 0, 0, minus 850, 864, 14, 0, 0, 14, 14, 100. Fourteen 100. Let's try that again. So they're the numbers I get for I1, I2, and I new. Seem pretty high, but that's probably okay. So then we need to get I new, which is that last one, and to find the short to find the Thevenin resistance, we just divide. So V equals IR, so R equals V on I. We divide V new by I new. Okay, so I'm just pulling out I new from the bottom right corner, and that's telling me that RTH is 22.5354. Let's see if that works for me. Yep, seems to like that one. And then the question is, what's VTH? What's the Thevenin voltage? That's going to be a little bit more work. Right, we're going to have to take our circuit, and we have to figure out the open circuit voltage. So how do we figure out the open circuit voltage? 24 and 450. And what were the other two? 414. Okay, and so how do we do that? Well,
So would you do nodal analysis, make a super node around the dependent voltage source, and find the voltage at the right node, and then that would be your Thevenin voltage, if you make the bottom your reference?
yeah, that might work. Why don't we look at doing that? Yeah, why don't we try that? So we'll make this node A, this node B, and then our KVL for the supernode will be VB minus VA equals 450 IX, and IX is just going to be VA, so that's going to be 450 times VA on 400. Okay, and then our KCL for the supernode is going to be IS minus IX. Let's make IR2 go that way. Minus IR2 equals 0. Right, and IS is 24 IX, which again is VA on 400 minus VA on 400 minus VB on 14 equals 0. Let's just see if we can rearrange this one. That's going to be minus 850 on 400 VA. If I take this around the other side, and then plus VB equals 0, and then I can do, what's that? That's that one becomes 23 on 400 VA minus 1 on 14 VB equals 0. I think that's going to come out to 0, but let's just check. Right, so that's minus 850 on 400. 1. 23 on 400. Minus 1 on 14. And 2 zeros. And I suspect that's going to give us so let's do that. So it's minus 850, 50 on 400, 1 0, 23 on 400, minus 1/14, 0. And sure enough, we get both VA and VB as 0. Which tends to happen when you have no independent sources, only dependent sources. Okay, so let me just quickly run through the others, then we'll have a short break, and then I'll make an attempt at quickly explaining the lab. And yeah, I don't know whether maybe I should actually spend some time on the topic I was supposed to walk through tonight. So let's see how we go. So problem 4. So we're going to find Norton's theorem, and again this one's got 2 independent sources, so we could probably use equivalent resistance to find RTH, and then to find the Norton current we just need to find the short circuit current. So we place a short over A and B and then analyze the circuit that way. Yeah, that'll work. We'll end up with, what's that? So if we place a short across A and B, that means R4 doesn't take part in the equations, right? Because it's the 2 paths going from A to B have a 0 resistance path and an R4 resistance path. So all the current's going to take the 0 resistance path. So that just ends up having 3 meshes: VS, R1, R2, R2, IS, R4, and IS and R3. And that should allow you to calculate the short circuit current, which will be the current in the middle loop there. Another Norton question, but this time with a dependent voltage source and an independent voltage source. So we've got to use short circuit current and open circuit voltage, or apply a voltage technique to find the Norton current. The Norton resistance. Might just as well use open circuit voltage, short circuit current. Short circuit current gives you IN. That combined with the open circuit voltage gives you RN. And question 6. So this one suggests you use source conversions. And what would I do to do source conversions here? I think what I'd do is I'd just convert Vs and R1 into a parallel current source and a parallel R1. That way R1 and R2 would be in parallel with R3 plus R4, right? R3 and R4, maybe. Well, you could certainly combine the resulting current source with IS to just get a single current source and a single resistance, which would be R1 in parallel with R2. And then you'd probably want to look at how to... Oh, then you'd probably turn that back into a Thevenin equivalent. With a voltage and R1 in parallel with R2 is the series resistance, which would then be going to R3 and R4. Yep, I think that'd be relatively straightforward to do it that way. That way you'd end up with a single independent source, which you could then use which would be your Norton current, and you could use equivalent resistance to find out what the Norton resistance is. Okay, let's take a 5-minute break, and I'll come back, do a quick thing with the new stuff and the lab. I think they're the two things I need to get going on. But let's just have a quick break. Okay. Let's let's see if we can get the let's see if we can get at least a couple of those done. So first of all, I'm just going to, like I said earlier, we're going to introduce inductors and capacitors, and inductors and capacitors give us complex impedances, which are like a resistance. So let's have a look at that. Okay, so up to a point, you've learnt everything you need to know about circuit analysis in this course already. All we're going to be doing from now on is taking all of that stuff that we already know and applying it to the case where instead of having real valued resistances, we have complex valued air quote resistances, close air quote. In reality, we don't call complex valued resistances, we call them impedances. So this is where we are, at least in the summer of 2019. And in this video, and maybe some follow-up ones with some work-throughs, we're going to talk about capacitance, inductance, reactance, and impedance, and how that all hangs together with what we've learnt to date. So far we've been working with resistance. And another word that we should start using is a thing called reactance. And reactance is a resistance that is purely imaginary, that is, it has no real component. And this should actually not say reactance. Let me fix that, the last line there. So when we have a complex valued resistance, we're going to call that impedance. So the complex value meaning it has a real part and it has an imaginary part. When that's no longer a resistance, it's going to be called an impedance. Okay, so let's just walk through the impedance of a resistor for now. Instead of having constant voltages and constant currents, we're going to be talking about time varying cosinusoidal voltages and currents. So our V of t is A cosine omega t plus theta in volts, and Ohm's law still applies, so V equals IR. So the current in our circuit here is A cosine omega t plus theta, all divided by the resistance R. Now we can write V of t on I of t, and we just get that. And then one thing we're going to be doing is we're going to, once we know what our operating frequency omega is, we're pretty much going to ignore it. We need to make sure we know what it is, because it's going to tell us what some of our impedances are, which we'll see shortly. But we're pretty much going to ignore it. So what we're going to be able to do, all we're going to do is we're going to use this shorthand, right? We're going to go from cos omega t plus theta, and we're just going to replace that with this 1 angle theta, and the same on the denominator, numerator and the denominator. And that means we can then cancel things out, and so we get that the impedance of our resistor, which is V on I, is just R. So Ohm's law still holds, so we should be reasonably happy with that. Capacitance gets a little trickier, right? For a capacitor physically is two conducting plates separated by a dielectric. So this gap here between the two plates is the dielectric. The air gap may not be air, but the gap. And if we apply a voltage, V equals A cosine omega t plus theta, then the relationship between V and the current is I, as a function of time, is equal to C dV dt. So the current is equal to the capacitance of the capacitor times the time derivative of the voltage. So if I take the derivative of A cosine omega t plus theta, I get minus A omega sine omega t plus theta. So the current is going to be given by minus A omega c sine omega t plus theta in amps. And we can do the same sort of thing. We can figure out what the impedance of the capacitor is by looking at V on I. So it's A cosine omega t plus theta divided by minus A omega c sine omega t plus theta. And then I need to remember that sine omega t plus theta is equal to cos omega t plus theta minus 90 degrees. And that means when I do my change from cos omega t to my phasor notation, that's what this is called. A magnitude and an angle is a phasor notation. I'm left with a theta minus 90 degrees instead of just theta degrees. And then I can cancel out my a's, and I'm left with minus 1 on omega c times 1 angle 90 degrees, which is minus j on omega c, which can also be written as 1 on j omega c. The reason is up here because 1 on j is equal to minus j. Okay, so there's the impedance of my capacitor, 1 on j omega c. I can do exactly the same for an inductor, except now my current is related to the voltage via this integral, 1 on L, integral V of t dt. So now my impedance is A cosine omega t plus theta divided by A on omega L sine omega t plus theta. And I can run through that same algebra to get that the impedance of my inductor, L, which is V on I, is just J omega L. So to summarize, for a resistor, its resistance, that is real component of its impedance, is R. Its reactance, which is the imaginary component of its impedance, is 0. So the total impedance is R plus J0. The units we use are in ohms. The inverse units are what we call conductance, and the units for that conductance is Siemens, denoted capital S. An inductor and a capacitor both have 0 resistance. The impedance of the reactance of an inductor is omega L. The reactance of a capacitor is minus 1 on omega C. So the total impedance of the inductor is J omega L. The total impedance of a capacitor is 1 on J omega C. The units of capacitance of C is a farad, denoted capital F. The units of L is the Henry, denoted capital H. The inverse of inductance is called reluctance. The inverse of capacitance is called elastance. And there's no specific SI units for their inverses, so the units are inverse Henry and inverse farad with a minus 1 to the H and minus 1 to the F. So in the next video I'm going to do some examples. I'm going to look at what the output voltage is here. This is just a voltage divider question. I'm going to look at what the current is here. This is just a current divider question. And I'm going to look at this sort of question, which can be solved using either mesh analysis or nodal analysis. But I'll do that in the next video. Okay, any questions about that so far? The key piece is the first thing you've got to do when you do any problem involving inductors and capacitors is to convert the inductance or capacitance into an impedance. So if it's an inductor, you need to know the frequency in radians per second. So you need to get J omega L, where L is the inductance and omega is the frequency. J is the square root of minus 1. Or if it's a capacitor, it's 1 on J omega C. Again, C is the capacitance value in farads. Okay, let's continue with the next two anyway, and I might leave the third one for later. Okay, so up to a point, you've learnt everything you need to know. Oops, let's try that again. I think I just restarted the same video. Let's go with that one instead. So here's the first example using impedances rather than resistances, and this is a simple voltage divider. One thing to note is our positive and negative here is different from here. So if we assume that this node is our reference node, then this node here is at minus VI because of the polarity of the supply. Then we need to look at the inductance. The inductance is 100 millihenries, but that's not our impedance. Our impedance is going to be J omega L for an inductor, and so we need to figure out what omega is, and we can see omega down here is 10,000 is the frequency in radians per second. So it's J 1000 times L, and L is 0.1, so that overall thing is just J 1000. And then our output voltage V out is equal to ZL, just using the voltage divider equation, on ZR plus ZL times, well, it's minus VI. And another thing we can do, once we've used the omega to calculate the impedances, we can then convert our voltage into a phasor notation or polar notation. So this is just 4 angle 45 degrees. So this will be minus 4 angle 45 degrees. So if we substitute all that in, we get J1000 on 1000 plus J1000 times minus 4 angle 45 degrees. Okay? And the way to put that into your calculator is, at least for this one, is we need to do minus 4 e to the j 45 on 180 times pi, because your calculator is probably going to assume everything is in radians. So let's see what that looks like on the calculator. And I've just done it here before, but let's go through it again. So we go minus 4 exponential I times 45 divided by 180 times pi. Okay, so that's minus 2.828 minus J 2.828, and we multiply that by J1000, or on your calculator it will be I1000, divided by 1000 plus I1000. And so we end up with minus 2.828 I. Okay, so our overall answer here is minus J 2.828. Okay, so if we think about that in our X and Y version, so this is the real component, this is the imaginary component, then minus J 2.828 is down in this direction. Let's just get a different color. Right, so our minus J 2.828 is down here. So the angle we have is 270 degrees. So a way to write this in polar form would be to write it as 2.828 angle 270 degrees. Okay, and that's the first example. It's a voltage divider using impedances rather than using just resistances. So here's another example. So I'm just going to continue with, I'll finish after the videos after this video, which is going to do a current divider example. There is a third example doing a more complicated, I think I did a mesh analysis example. Any questions so far? Okay, we'll continue. Of using impedances rather than just resistances. In this case it's for a current divider rather than a voltage divider. Okay, so again we've got to figure out, we have our, this time we've got a capacitor rather than an inductor, and given our input current we have to figure out what this output current is. And as we know, let's just get a different color. We know this node here, right? This is an area of constant voltage. So we know that it's a node, and we can see that the current into the node, and let's just draw this as IR, we can see that II minus IR, because IR is coming out of the node, minus I out is equal to 0. So that's Kirchhoff's current law. Okay, so now let's try and figure out, and so we've got impedances, so we have to figure out what ZC is. And as you should be aware from the lecture, ZC is 1 on J omega C. So let's figure out what omega is. Omega is 1000 in this case, so ZC is 1 on J 1000 for omega times C, and C is 1 and it's microfarads, so that's 1 by 10 to the minus 6. So that's 10 to the minus 6. Okay, so that means that that's going to be 1 on J by 10 to the minus 3. Or if you work it out, it's going to be minus J 1000. Remember, 1 on J is equal to minus J. Okay, so now we have ZC, so now we can figure out what I out is. So let's go, I out is just going to be equal to the impedance in the other branch times the sum of the impedances, right, times the input current. And that's another thing we've got to figure out. What's the input current? Well, we've used the frequency, so let's just convert this into a phasor notation, and I'm going to use amps rather than milliamps. So that's 0.4 angle minus 30 degrees. Okay, so now we can fill it all in. We've got 500 as our ZR, it's over here, and oops, we've got a minus J 1000 there, and then it's times 0.4 angle minus 30. And then we should be able to just plug that into our calculator. So let's figure out where the calculator is. So that's here. And so we can do 500 divided by 500 minus I times 1,000 times 0.4 times E to the minus 30 on 180 times pi. And so there we get our answer, right? It's 0.047. So let's write this. Let's write it out in right. So it's so it's 0.04739 plus J 0.09478, and that is in amps. If we wanted to write that in milliamps, which we probably should, then it's going to be 47.39 plus J 94.78 milliamps. And the other thing we should be able to do is to convert that into polar form. But I'll leave that for the next video. Okay. I'm not going to go through the next video on right now. Have a look at it. I think we should probably leave it there for this evening. I was trying to get... Okay, so here's the third worked example. I was trying to get through to talk a little bit about the lab. I'm not going to have time. What I'm going to do is tomorrow I'm going to put together a video about the lab. I thought I had one, but I couldn't find it earlier. I'll put together a video about the lab and I'll push off the scheduled date from tonight until next week, next Monday. That way you'll have time to get the lab done correctly and still manage to get that bonus. Okay, any questions so far? If not, let's leave it there for this evening. Thanks for your time.